Here's something that should keep you up at night, but probably won't. Right now, as you're reading this, roughly 100 billion neutrinos from the sun just passed through your body. In the time it takes you to blink, another 100 billion will follow. They are travelling at nearly the speed of light, and they don't even notice you're there. Your entire body of bones, organs, all of it, is essentially invisible to them, offering no more resistance than empty space. By the time you finish listening to this, about 10 quadrillion solar neutrinos will have passed through you, and you won't have felt a single one. And here's the thing that blows my mind. This isn't some exotic phenomenon happening in a particle accelerator. This is just Tuesday. This is reality, happening constantly everywhere to everyone, completely unnoticed. Now, take that sense of invisible, pervasive reality and apply it to something even more extreme, something that utterly defies our everyday intuition, a black hole. We've all heard the term, seen the images, maybe even grasped the basic idea. It's a region of space-time where gravity is so intense that nothing, not even light, can escape. It's the ultimate cosmic drain, a one-way street to, well, we don't quite know where. But here's the paradox that truly unlocks the next level of wonder. The fundamental equations that govern our universe, the very fabric of physics as we understand it, are often reversible. If you can run a movie forward, you can often run it backward. If a black hole is a region that only absorbs, what happens if you mathematically reverse that process? What if you run the cosmic movie backward? The answer, surprisingly, is something called a white hole. If a black hole is a cosmic vacuum cleaner, a white hole would be a cosmic geyser, an object from which matter and energy can only emerge, never enter. It's a region of space-time that forcefully expels everything, a fountain of the universe rather than a sink. And while black holes are now undeniably real, observed and studied, white holes remain tantalizingly theoretical, a ghostly mirror image predicted by the same equations that describe their ravenous counterparts. They might be the most mind-bending, counterintuitive, and perhaps the most profoundly significant objects the universe could possibly harbour. If you're enjoying this journey through science, hit that like button and subscribe so you don't miss future episodes. And I'm always curious, drop a comment letting me know what city and time zone you're watching from. There's something special about knowing this story is reaching people all over the world, connecting us through the shared wonder of the cosmos. Over the next 10 chapters, we are going to dive deep into this fascinating cosmic mystery. We'll start with the familiar, then twist our understanding into new dimensions, slowly building a picture of what white holes are, how they might exist, and what they could mean for everything we thought we knew about the universe. Let's start with a concept that has captivated scientists and laypeople alike for decades: the black hole. We often hear it described as a cosmic vacuum cleaner, or a region where gravity is so strong that nothing, not even light, can escape. But here's what's truly mind-blowing and often overlooked. A black hole isn't just a thing sitting in space. It's a profound distortion of space itself and of time. It's not a hole in space, but a hole of space, a fundamental rearrangement of the very fabric of reality. Understanding this distinction is the first step to truly grasping the bizarre nature of these objects, and ultimately, to contemplating their theoretical opposites. To truly understand a black hole, we need to strip away some of the popular imagery and go back to basics. It all starts with gravity. Isaac Newton described gravity as a force, an invisible pull between any two objects with mass. The more massive the objects and the closer they are, the stronger the pull. We experience this every day. The Earth's gravity keeps us grounded, and the Moon's gravity tugs at our oceans, creating tides. Newton's description worked incredibly well for centuries, explaining everything from falling apples to planetary orbits. But then came Albert Einstein, who, in his theory of general relativity, completely reconceptualized gravity. Einstein didn't see gravity as a force in the traditional sense, but as a curvature of space-time. Imagine space-time as a gigantic, flexible sheet, like a trampoline. If you place a bowling ball on that sheet, it creates a dip. A marble rolling past the bowling ball isn't pulled by a force, it simply follows the curve created by the bowling ball. Planets orbiting the Sun aren't pulled by a force, they're following the curves in space-time created by the Sun's immense mass. This is a crucial mental model. Gravity isn't a pull, it's a push from the geometry of the universe itself. Now, let's bring in two other fundamental concepts: mass and density. Mass is simply the amount of stuff an object contains. Density, however, is mass packed into a given volume. A feather has very little mass and very low density. A brick has more mass and higher density. But imagine taking all the mass of that brick and compressing it into the size of a sugar cube. Its density would skyrocket. The more mass you squeeze into a smaller and smaller volume, the denser it becomes, and the more profoundly it warps the space-time around it. This warping leads directly to the concept of escape velocity. Every object with mass has an escape velocity, the speed an object needs to travel to break free from its gravitational pull. For Earth, escape velocity is about 11.2 kilometers per second, or roughly 25,000 miles per hour. That's why rockets need powerful engines to get into space. For the Moon, it's much lower. For the Sun, it's much higher. The more massive and dense an object, the higher its escape velocity. Now picture an object so incredibly dense that its escape velocity exceeds the speed of light itself. The speed of light, approximately 272,458 meters per second, about 186,282 miles per second, is the absolute speed limit of the universe. Nothing can travel faster. If an object's gravitational pull is so immense that even light, moving at this ultimate speed, cannot escape, then literally nothing can escape. This is the defining characteristic of a black hole. This isn't just a theoretical construct, it's a direct consequence of Einstein's equations. When a star much more massive than our Sun, typically at least 8 to 10 times the Sun's mass, runs out of nuclear fuel, it can no longer support itself against its own gravity. The core collapses inward, crushing itself down to an unimaginably dense point. If this collapse continues unchecked, it forms a black hole. The key boundary around a black hole is called the event horizon. This isn't a physical surface you could stand on. It's a purely conceptual boundary in space-time. Imagine it as a cosmic waterfall. If you're above the waterfall, you can still paddle upstream. But once you cross the lip of the falls, no matter how hard you paddle, the current is stronger than your maximum speed and you're inevitably carried over the edge. For a black hole, the current is the curvature of space-time and the maximum speed is the speed of light. Once anything, be it light, matter, or even information, crosses the event horizon, it's on an irreversible one-way trip inward. What happens inside the event horizon? This is where our current understanding of physics starts to break down, but the equations point to something called a singularity. This is not just a very small, very dense object, it's a point of infinite density and zero volume, a place where the laws of physics as we know them cease to apply. All the mass of the black hole is theorized to be compressed into this single, infinitely tiny point. It's important to understand that we can't actually see the singularity, because it's hidden behind the event horizon. The event horizon protects us from its truly bizarre nature, a concept sometimes called the cosmic censorship hypothesis. Furthermore, black holes are surprisingly simple objects, according to the Whit-No-Hare theorem. Once a black hole forms, it quickly settles down into a state that can be completely described by just three properties: its mass, its spin, or angular momentum, and its electric charge. Everything else about the star that formed it, its composition, its magnetic fields, its irregularities, gets smoothed out and lost once it collapses beyond the event horizon. It's as if the black hole has no hair to distinguish it from any other black hole with the same three properties. This elegant simplicity is one of the most astonishing predictions of general relativity. The implications of black holes extend far beyond their immediate vicinity. They are not merely cosmic curiosities. They are fundamental architects of the universe. Supermassive black holes, millions or even billions of times the mass of our Sun, reside at the centers of nearly all large galaxies, including our own Milky Way. They play a crucial role in galaxy formation and evolution, influencing the birth of stars and the distribution of matter across vast cosmic scales. Our own supermassive black hole, Sagittarius A, is a quiescent giant, but in other galaxies, these behemoths can actively devour surrounding gas and dust, emitting incredible amounts of energy as quasars, outshining entire galaxies. Black holes also warp time in profound ways. This phenomenon, known as gravitational time dilation, means that clocks tick slower in stronger gravitational fields. Near a black hole, this effect becomes extreme. An observer far away would see a clock near the event horizon ticking slower and slower, eventually appearing to freeze entirely as it approaches the boundary. From the perspective of someone falling into the black hole, however, their own clock would tick normally, but they would see the entire future of the external universe flash by in an instant as they crossed the event horizon. This isn't just a theoretical oddity. Time dilation is a real effect precisely measured and accounted for in technologies like GPS satellites. The existence of black holes, predicted by Einstein's equations in 1916, was initially met with skepticism. It took decades of theoretical refinement and, crucially, observational evidence to confirm their reality. From the discovery of X-ray binaries like Cygnus X1 to the direct detection of gravitational waves from colliding black holes by LIGO, and finally the stunning direct image of the supermassive black hole MD7 by the Event Horizon Telescope, black holes have transitioned from mathematical curiosities to undeniable cosmic realities. They force us to confront the limits of our intuition and the profound elegance of the universe's governing laws. So we've established a solid understanding of what a black hole truly is, a region of space-time so profoundly warped that nothing can escape its grip, defined by an event horizon and culminating in a singularity. We've seen how its properties, mass, spin and charge, are elegantly simple, yet its effects on space and time are anything but. This detailed picture of a black hole, this cosmic sink, is absolutely essential, because now that we understand the ultimate one-way street inward, we are ready to peer even deeper into the equations of general relativity, to run the cosmic film backward, and to seriously consider the possibility of a theoretical object that is its perfect, mind-bending opposite, a region of space-time from which nothing can ever enter, but from which everything is relentlessly expelled. That journey begins as we delve into the nature of the event horizon itself. Okay, so we've journeyed deep into the heart of the cosmic sink, haven't we? We've seen how black holes, those voracious gravitational behemoths, warp space-time into an inescapable one-way street, where everything, light, matter, even the fabric of reality itself, plunges inward towards an unknowable singularity. It's a profound, humbling and utterly mind-bending reality, confirmed by observation after observation. But here's where the real intellectual adventure begins, because if the universe is a place of balance, of action and reaction, of inverse operations, then what, my curious friends, is the opposite of that cosmic sink? What's the celestial counterpoint to the black hole's insatiable appetite? Enter the whole white hole. Imagine, if you will, not a cosmic drain, but a cosmic geyser, Not a region of space-time that pulls everything in, but one that violently expels everything out. That's the core, exhilarating concept of a white hole. It's a theoretical beast, a mathematical marvel, and a phenomenon so profoundly strange that it forces us to rethink everything we thought we knew about the universe. Where a black hole is a point of no return in, a white hole is a point of no return out. Think of it like this. If a black hole's event horizon is a waterfall you can only fall down, a white hole's event horizon is a waterfall you can only be ejected from, unable to ever approach its source. Anything that tries to enter a white hole from the outside is instantly, catastrophically, and irrevocably pushed back out. Matter, energy, light, all of it streams away from this mysterious region, never towards it. It's not emission-only zone, a cosmic fountain that continually gushes forth. Now, why would such a bizarre entity even be considered? The answer lies, as so often in the cosmos, in the elegant equations of Albert Einstein, specifically his general theory of relativity. Remember how those equations describe gravity not as a force, but as the curvature of space-time? Well, here's the kicker. Those same equations are, for the most part, time-symmetric. What does that mean? It means that if you take a movie of a black hole forming and devouring matter, and then you play that movie backward, the laws of physics, as described by Einstein, don't bat an eye. They say, sure, that's a perfectly valid solution. And what do you see when you play a black hole movie backward? You see matter and energy erupting from a region of space-time rather than falling into it. You see a white hole. This time reversal symmetry is a powerful concept in physics. Many fundamental laws, like Newton's laws of motion or Maxwell's equations for electromagnetism, work just as well if you reverse the direction of time. A ball thrown up comes down, in reverse a ball comes up from the ground. A planet orbits a star, in reverse it orbits the same way. The universe, at its most fundamental level, doesn't seem to care which way the arrow of time is pointing, so when physicists found solutions to Einstein's equations that described a black hole, they naturally wondered about the time-reverse version, and there it was, the white hole. Mathematically, they are two sides of the same coin, flip sides of the same space-time geometry. They are the mathematical inverse of each other. Let's dive a little deeper into its characteristics. Just like a black hole, a white hole would possess an event horizon. But this isn't an event horizon of no escape. It's an event horizon of no entry. Imagine a barrier around a region of space. If you're outside a black hole's event horizon, you can escape if you're fast enough. Cross it, and you're trapped forever. With a white hole, if you're outside its event horizon, you can move freely. But try to cross into that boundary, and the very fabric of space-time rebels, pushing you back out with an irresistible force. There is no path inward. This boundary is an outgoing null surface, meaning light rays can only travel outward from it. And what about the singularity? If a black hole has a singularity at its heart, a point of infinite density and curvature where all matter is crushed, what would a white hole have? Well, if we follow the time-reversed logic, a white hole's singularity would be a point of creation, or rather a point from which matter and energy emerge. It's not a destination but a source. This is where things get truly mind-bending, because it implies a continuous, spontaneous generation of stuff pouring into our universe from somewhere. The no-hair theorem we discussed for black holes, that they are characterized only by mass, spin, and charge, would also theoretically apply to white holes. They too would be remarkably simple objects, their complexity swallowed by the geometry of space-time. So what if white holes are such elegant mathematical solutions, such perfect cosmic opposites? And if Einstein's equations permit them, why haven't we seen one? This is the crucial question, and it's where the theoretical elegance clashes with the messy reality of our universe. Here's the thing. While mathematically possible, white holes are generally considered unstable and unphysical by most astrophysicists. First, consider the stability issue. A black hole is stable because gravity is always attractive. Anything that falls in just adds to its mass and makes it stronger. But a white hole is constantly expelling matter and energy. What if even a tiny bit of matter, a single photon, tried to enter its event horizon? The theory suggests it would be violently pushed out. But if by some quantum fluke or external pressure anything were to make it past that boundary, the delicate balance that defines the white hole would immediately collapse. It would essentially become a black hole, or simply cease to exist as a distinct entity. It's like trying to keep a geyser perfectly contained. The slightest disturbance could change its nature. Second, and perhaps more fundamentally, is the issue of formation. How would a white hole even come into being? Black holes form naturally from the gravitational collapse of massive stars. We understand the process, we see the evidence. But there's no known physical process in our universe that could lead to the formation of a white hole. They don't seem to have a parent event. You can't just reverse a star's collapse to get a white hole. That would require matter to spontaneously uncollapse and then start exploding outward. That violates our understanding of causality and thermodynamics. This brings us to the second law of thermodynamics. This fundamental law states that the entropy and disorder of a closed system can only increase over time, or at best stay the same. Black holes increase entropy by swallowing information and increasing the total disorder of the universe, though Hawking radiation adds another layer to this, which we'll explore later. White holes, by continuously spewing out highly ordered matter and energy, would seem to locally decrease entropy, which is a big red flag for physicists. It's like watching a broken glass spontaneously reassemble itself. It's just not how our universe seems to work. So while the math is beautiful, the physics of our observed universe presents significant hurdles. It's a bit like having a perfectly valid mathematical solution for a perpetually shrinking sphere that gets smaller and smaller forever, but then realizing that in the real world, atoms have a minimum size. The math works, but reality imposes constraints. Despite these challenges, the concept of white holes isn't entirely dismissed. Some theories propose they might be primordial white holes, relics from the very early universe, perhaps created during the Big Bang itself. If they formed then, they wouldn't need a specific formation mechanism. Now, they would simply be ancient existing features of space-time. Others wonder if they could be connected to exotic phenomena like wormholes, acting as an exit point from another region of space-time or even another universe. These are tantalizing ideas, pushing the boundaries of what we consider possible. For now, white holes remain firmly in the realm of theoretical physics. They are the unobserved, the unconfirmed, the ghost in Einstein's machine. They are the ultimate what-if of cosmic mechanics. They force us to confront the limits of our understanding and ask whether the universe, in its profound strangeness, might hold secrets that defy our everyday intuition and even our most cherished physical laws. We've explored the cosmic sink, the black hole, and now we've peered into the theoretical maw of its opposite, the cosmic geyser, the white hole. We understand why they are mathematically compelling and why they are physically problematic. But the journey doesn't end here. The very existence of this theoretical possibility, this anti-black hole, opens up a universe of questions. What if they do exist? What would they look like? And how might they connect to the greatest cosmic mystery of all, the Big Bang itself? Next, we're going to dive deep into the fascinating, often contradictory, and sometimes downright bizarre ideas that connect white holes to the very beginning of everything. Get ready, because the universe is about to get even stranger. We've journeyed deep into the heart of black holes, those cosmic devourers, and then peered into the theoretical mirror image. The white hole, a geyser of creation, a region of space-time that only emits. But as we concluded our last exploration, we touched upon the immense hurdles preventing white holes from being anything more than elegant mathematical solutions to Einstein's equations. They are, for all intents and purposes, considered unphysical. But why? And what if, just what if, there's a way around these seemingly insurmountable obstacles? This is where the true adventure begins, where the boundaries of known physics get delightfully blurry. Remember those 3 big strikes against white holes? First, their some instability. Imagine trying to hold back a tsunami with a sieve. Any tiny disturbance, any speck of matter attempting to enter that no-entry event horizon would theoretically cause the entire structure to collapse. It's like trying to keep an explosive balloon perfectly inflated in a hurricane. Second, the lack of a formation mechanism. Black holes are born from the death of massive stars, a clear, observable process. White holes? We have no known cosmic recipe for their creation. And third, the pesky second law of thermodynamics, which dictates that entropy, or disorder, in a closed system must always increase or stay the same. A white hole, constantly spewing out matter and energy, would locally decrease entropy within its immediate vicinity, a concept that makes most physicists shudder. These are not minor quibbles. These are fundamental challenges to our understanding of the universe. And yet the mathematical elegance of white holes, their sheer possibility within the framework of general relativity, continues to tantalize. It's a bit like finding a perfectly symmetrical, beautiful, but utterly impractical blueprint for a machine that seems to defy all known engineering principles. You can't build it, but you can't quite throw away the blueprint either. Here's another layer to the unphysical argument, one that delves into the very fabric of how physicists prefer their singularities. In a black hole, the dreaded Ball singularity, that point of infinite density where the laws of physics break down, is safely tucked away behind the whole event horizon. You can't see it, you can't interact with it, you can't even get information from it once you're outside the event horizon. This concept is so central to theoretical physics that it has a name, the Paul cosmic censorship hypothesis. It's not a proven theorem, but rather a powerful guiding principle, a belief that nature censors naked singularities. A naked singularity is one that's not hidden by an event horizon, one that would be visible and directly interactable, potentially allowing for all sorts of paradoxes and violations of causality. Now, think about a white hole. Its event horizon is a boundary of no entry, meaning anything inside it is forced out. If you were to look at a white hole, you would, in theory, be looking at the singularity itself, or at least at the region where matter and energy are emerging from it. This would, by definition, be a naked singularity. It would be a direct window into a place where our physics fails, a cosmic anomaly that could potentially unravel the very consistency of the universe. Most physicists prefer their singularities modest and well-dressed, thank you very much, hidden behind the veil of an event horizon. The cosmic censorship hypothesis essentially says no naked singularity allowed in this universe. And if white holes inherently require a naked singularity, then that's another strike against their reality. So, with all these strikes against them, why do we even bother talking about white holes? This is where the real fun begins, where theoretical physicists, unbound by direct observation yet, let their imaginations soar, trying to find ingenious ways to make the impossible, well, possible. It's about pushing the boundaries of what we understand and exploring the what-ifs that might just unlock new secrets of the cosmos. One of the most exciting and promising avenues for white hole existence comes from the wild, wonderful world of a quantum gravity. Remember, general relativity is fantastic for the large-scale universe, for planets, stars and galaxies, but at the incredibly tiny scales, at the quantum level, and especially at the heart of a singularity, general relativity breaks down. This is why physicists are desperately trying to develop a theory of quantum gravity, a unified theory that can describe gravity at all scales. Enter per loop quantum gravity, LQG. This is one of the leading contenders for a theory of quantum gravity, and it offers a truly mind-bending possibility for white holes. In LQG, space-time isn't smooth and continuous. It's made up of tiny, discrete loops, like a fabric woven from incredibly fine threads. This quantization of space-time changes everything, especially when you consider the extreme conditions inside a black hole. What happens to matter that falls into a black hole? According to general relativity, it hits the singularity and is crushed out of existence, or at least beyond our comprehension. But LQG suggests something different. Instead of being crushed into an infinitely dense point, the quantum nature of space-time imposes a limit on how dense matter can become. Imagine trying to compress something to an infinite density. LQG says, nope, there's a quantum flaw. So what happens when matter reaches this maximum density inside a black hole? LQG proposes a quantum bounce. Instead of collapsing to a singularity, the matter and space-time inside the black hole rebound. This isn't just a gentle bounce, it's a violent, explosive reversal. And what does this rebound create? You guessed it, a white hole. Think of it like this. A black hole is a cosmic vacuum cleaner sucking everything in. But according to LQG, at its very core, it hits a quantum wall, and instead of stopping, it bounces, transforming into a cosmic geyser, a white hole, spewing out all the matter and energy it previously swallowed. This process is often called black hole evaporation, or, more specifically, black hole to white hole transition. It's a slow, drawn-out affair taking billions upon billions of years, far longer than the current age of the universe for typical stellar mass black holes. So we're not talking about seeing this happen next Tuesday. This quantum bounce mechanism offers a solution to several of the white hole problems. First, it provides a formation mechanism. White holes are born from the death of black holes, or rather, their quantum transformation. Second, it potentially addresses the singularity problem. Instead of an infinitely dense point, you have a region of extreme but finite density, which then expands outward. And while it doesn't directly solve the instability or entropy issues in the traditional sense, it reframes the white hole as a phase in a black hole's life cycle, a quantum tunneling event that allows for a temporary localized reversal of sorts. It's a truly revolutionary idea, one that connects the beginning and end of these cosmic behemoths. But wait, there's more. Remember how we briefly touched on wormholes in the last chapter? Those theoretical tunnels through space-time connecting distant points or even different universes. Well, some models of wormholes, specifically the Einstein-Rosen bridges, inherently feature a black hole at one end and a white hole at the other. Imagine space-time as a piece of paper. A black hole punches a hole in it, creating a deep well. A white hole, in this analogy, would be like a corresponding bulge on the other side of the paper, or perhaps another sheet entirely. Matter could theoretically fall into the black hole end of the wormhole, traverse the throat, if it's stable and traversable, which is a huge if, and emerge from the white hole end. This concept is wildly speculative, often requiring exotic matter with negative energy density to keep the wormhole open, but it elegantly links black holes, white holes, and the mind-bending possibility of interstellar or even interuniversal travel. Of course, the white hole end of a wormhole would still face the issues of instability and the no-entry event horizon, meaning it would be a one-way street out. You couldn't just casually stroll into a white hole to see what's on the other side. You'd have to come from the other side. This makes wormholes even more enigmatic, but the connection between black holes and white holes through these theoretical bridges is a powerful conceptual tool for physicists. Beyond the quantum bounce and wormholes, there's another, even more ancient idea: primordial white holes. What if, instead of forming from black holes, some white holes were created during the very early universe, in the chaotic, high-energy conditions right after the Big Bang? Just as tiny primordial black holes might have formed from density fluctuations in the nascent cosmos, perhaps their white hole counterparts did too. These would be incredibly still, perhaps microscopic, and would have been spewing out energy since the dawn of time. If they exist, they would be incredibly difficult to detect, but their emissions might leave subtle traces. So if white holes do exist in any of these theoretical forms, how would we actually find them? What would a white hole look like? And this is where the rubber meets the road, or rather, where the theory meets the telescope. A white hole, by its very nature, would be an incredibly bright and energetic object. It's constantly emitting, after all. We might observe them as incredibly powerful bursts of radiation, perhaps even gamma-ray bursts, GRBs, some of the most energetic events in the universe. GRBs are often associated with the collapse of massive stars or the merger of neutron stars, but some of their properties remain mysterious. Could some of the more unusual GRBs be the signature of a white hole burping out matter and energy? It's a tantalizing thought. Another possibility involves looking for unique radiation signatures. If a white hole is constantly spewing out matter, that matter would interact with the surrounding interstellar medium, creating specific patterns of light and energy that could be distinguishable from other cosmic phenomena. We'd be looking for something that looks like an explosion, but one that's continuous or has very specific emission characteristics that don't fit known astrophysical processes. However, the observational challenge is immense. The universe is full of incredibly energetic phenomena, and distinguishing a white hole from a supernova, an active galactic nucleus, or a quasar would be incredibly difficult. We would need very precise measurements and a deep understanding of what a white hole's emissions should look like, based on the specific theoretical model we're trying to prove. For now, white holes remain firmly in the realm of theory, a beautiful, mathematically consistent but stubbornly elusive concept. They represent the frontier of our understanding, a place where general relativity clashes with quantum mechanics, and where our wildest imaginings about the cosmos might just hold a kernel of truth. The journey to understand them isn't just about finding another exotic object in space. It's about pushing the very limits of physics, challenging our assumptions, and perhaps one day, unveiling a deeper, more interconnected universe than we ever thought possible. The universe, you see, is under no obligation to be simple, and sometimes the most elegant mathematical solutions, even those that seem impossible, are just waiting for us to catch up to their reality. The question isn't whether white holes can exist, but whether the universe chose to make them. And that, my friend, is a mystery worth chasing. So we've journeyed through the mind-bending reality of black holes and dipped our toes into the tantalizing yet problematic theoretical waters of white holes. We've wrestled with their inherent instability, the lack of a clear formation mechanism from stellar collapse, and the nagging issue of a naked singularity that just doesn't sit right with our current understanding of the universe. We've even touched on the idea of a quantum bounce inside black holes, potentially transforming them into their radiant counterparts. But what if we're looking for them in the wrong place or at the wrong time? What if white holes aren't born from the dramatic death throes of a star, but from something far, far grander? Something that predates stars, galaxies, and even time as we know it. Imagine, if you will, the very earliest moments of our cosmos. Not the universe as it is now, vast and sprawling, but a universe compressed into an unimaginably small, hot and dense state. We're talking about the Big Bang. This is where the concept of what primordial white holes enters the stage, a truly fascinating and deeply speculative idea that attempts to address some of the biggest questions surrounding these cosmic geysers. If white holes can't form now from collapsing stars, perhaps they formed then in the crucible of creation itself. Think back to the Big Bang. Our universe didn't just appear as a perfectly uniform, smooth expanse. Oh no, it was a chaotic quantum soup, filled with tiny, fleeting fluctuations in energy and density. These aren't just minor ripples. These are the seeds from which all the large-scale structures in our universe, galaxies, galaxy clusters, vast cosmic webs, eventually grew. Now here's where it gets wild. What if amidst these primordial fluctuations, some regions became so incredibly dense, so utterly compressed, that instead of collapsing into black holes, they somehow bounced into existence as white holes? Not a bounce from an existing black hole, but a bounce from the initial conditions of the universe itself. My mind absolutely reels trying to picture it. Consider this. If the universe began from an incredibly dense state, and if quantum gravity effects truly become dominant at such extreme scales, then perhaps the very fabric of space-time could have allowed for the spontaneous emergence of these exotic objects. It's a bit like asking what came before the Big Bang, a question that pushes the boundaries of physics and philosophy. Some theories propose that our universe itself could be the white hole exit point of a prior universe's black hole collapse, a cosmic reignition, a grand universal quantum bounce on the largest possible scale. If primordial white holes did form during the Big Bang, they would be fundamentally different from the theoretical white holes we've discussed so far. They wouldn't be the time-reversed counterparts of stellar mass black holes. Instead, they'd be relics, fossilized remnants of the universe's infancy. And crucially, they wouldn't necessarily suffer from the same instability issues as their stellar mass cousins. Why? Because they wouldn't have formed from a collapse that could be easily disrupted. They would have been there from the start, baked into the initial conditions of the cosmos. Imagine these tiny, dense knots of space-time, each with its own outward-pushing event horizon scattered throughout the early universe. What would they be like? Unlike the massive black holes we observe today, gobbling up stars and gas, these primordial white holes would likely have been incredibly small, perhaps even microscopic, yet possessing immense mass. They would be like cosmic time capsules, slowly, inexorably releasing their contents over billions of years. And this leads us to another truly captivating idea. Could these primordial white holes be a component of dark matter? We know dark matter makes up about 27% of the universe's mass, and we still don't know what it is. It doesn't interact with light, it doesn't emit or absorb radiation, but its gravitational influence is undeniable. If microscopic primordial white holes exist, they would be incredibly dense, non-luminous, and would exert gravitational pull. They fit the bill in some intriguing ways. However, there's a catch, as there always is in theoretical physics. If they were truly microscopic and numerous enough to account for dark matter, they would also need to be very stable. And if they're constantly expelling matter and energy, even slowly, that would eventually become observable. So how might we detect these ancient reclusive objects? If they are indeed slowly spewing out matter and energy, their signatures would be subtle, spread out over cosmic timescales. We wouldn't see a sudden, brilliant flash like a typical supernova or even a short gamma ray burst from a neutron star merger. Instead, we might be looking for a persistent, low-level emission of particles or radiation that doesn't seem to originate from any known source. think of it less like a geyser and more like a slow, steady seep, a drip, drip, drip over billions of years. One tantalizing possibility ties into the very oldest stars in our universe. These are the population 3 stars, the first generation of stars to form, composed almost entirely of hydrogen and helium, without the heavier elements forged in subsequent stellar generations. We've never directly observed a population 3 star, but we know they must have existed. Could the formation of some of these ancient stars, or even the peculiar activity of some early galaxies, be influenced by the slow, gentle expulsion of matter from a nearby primordial white hole? It's a long shot, but it's the kind of cosmic detective work that keeps astrophysicists up at night. Another angle brings us back to those energetic bursts, gamma-ray bursts, GRBs. While we discussed how distinguishing a white hole GRB from a known black hole or neutron star event is incredibly challenging, primordial white holes might offer a different kind of signature. If a very small primordial white hole were to finally finish its expulsion or undergo some final rapid phase transition, it could produce a unique, short-lived burst that defies conventional explanation. The key here is not just a GRB, but a GRB with very specific anomalous characteristics, perhaps an unusual energy spectrum, or a lack of an obvious progenitor star, or even a peculiar afterglow that doesn't fit standard models. The quest for these primordial relics also pushes us to consider the cosmic censorship hypothesis again. Remember, this hypothesis states that all singularities in our universe should be hidden behind an event horizon, preventing them from being naked and exposing the bizarre, unpredictable physics of infinite density to the rest of the cosmos. A white hole's singularity, by its very nature of expelling matter, is often considered naked because its event horizon prevents entry, not exit. But if primordial white holes were born with the universe rather than from a collapse, perhaps their nakedness is less problematic in the context of the early universe's extreme conditions. Or perhaps their existence would be a direct challenge to the cosmic censorship hypothesis itself, forcing us to rethink one of the fundamental pillars of general relativity. And that, my friends, is why this conversation is so important. The very idea of white holes, especially primordial ones, forces us to confront the limits of our current understanding. It's not just about finding a new type of object, it's about potentially uncovering a missing piece in the grand puzzle of cosmic evolution. What if the universe isn't just expanding outward from a single point, but is also subtly being fed by these ancient hidden fountains of matter and energy? Could they contribute to the ongoing creation of new structures, or even influence the overall expansion rate of the universe? It's a tantalizing thought that connects these theoretical oddities directly to the biggest cosmological questions we face today, including the mystery of dark energy, which is driving the accelerated expansion of the universe. Could some form of white hole phenomenon be subtly contributing to this cosmic push? It's a highly speculative leap, but in the realm of theoretical physics, no stone is left unturned. The search for primordial white holes is a quiet, persistent one. It involves poring over vast amounts of astronomical data, looking for anomalies, for signatures that don't fit the expected patterns. It means pushing the boundaries of our theoretical models, trying to understand how quantum gravity behaves at scales we can barely comprehend. It's a journey into the deepest, most fundamental questions about where everything came from and what the ultimate fate of our universe might be. Ultimately, whether they exist as the exit wounds of black holes, the far side of wormholes, or as ancient relics of the Big Bang, white holes remain a profound theoretical challenge and an intoxicating mystery. They are a testament to the incredible power of Einstein's equations, which, when pushed to their limits, unveil a universe far stranger and more wonderful than we could ever have imagined. And the fact that we're still actively exploring their possibility, despite the immense theoretical hurdles, speaks volumes about the insatiable curiosity that drives us to understand the cosmos. The universe, it seems, always has another surprise up its sleeve. So we've explored the wild, mind-bending theories that suggest white holes could exist, quantum bounces turning black holes inside out, wormholes offering cosmic shortcuts, or even primordial white holes lurking since the dawn of time. But here's the kicker, the ultimate question that brings us back to Earth, or rather, to our telescopes and detectors. How would we ever find one? Imagine for a moment the sheer audacity of the task. We're talking about an object that by its very nature is constantly spewing out matter and energy, yet its event horizon prevents anything from entering. It's like trying to photograph a geyser that only erupts, but you can't get close enough to see the source, and its eruptions look suspiciously like every other violent cosmic phenomenon. The challenge is immense, a cosmic needle in an astronomical haystack. A white hole's signature, its unique fingerprint, would be subtle, complex, and potentially indistinguishable from other energetic events we already observe. Think about it. Supernovae explode, gamma-ray bursts ignite, active galactic nuclei blaze with incredible power. All these phenomena involve massive expulsions of energy and matter. How do we differentiate a garden-variety cosmic explosion from the signature of something truly revolutionary, a white hole? One of the most promising avenues for detection, if primordial white holes are indeed a reality, lies in their potential influence on the early universe. If these cosmic geysers formed from extreme density fluctuations shortly after the Big Bang, they wouldn't just sit there idly. They would have been active, spewing out their contents into the nascent cosmos. Picture it. Localized fountains of particles and energy erupting into the primordial soup. What kind of imprint would that leave? Perhaps we might find subtle, persistent emissions that don't quite fit the profile of any known astrophysical object. Instead of a single cataclysmic burst, a white hole might exhibit a sustained output that slowly fades over billions of years. Think of it less like a firecracker and more like a slowly deflating balloon of pure energy, leaking its contents into space. Could we detect a faint diffuse glow, a persistent whisper in the cosmic background radiation that we've previously dismissed as noise, but which upon closer inspection reveals a unique spectral signature? And what about those gamma-ray bursts, GRBs, we mentioned? These are the most powerful explosions in the universe, often linked to the collapse of massive stars or the merger of neutron stars. But what if some of them, just a tiny fraction, aren't caused by those familiar processes? What if a white hole, particularly a primordial one, could manifest as a unique type of GRB? Perhaps one that lacks the characteristic precursor events we often see with supernovae, or one with an energy profile that defies our current models. Imagine a sudden, inexplicable burst of high-energy radiation from a region of space that appears otherwise empty, with no collapsing star or merging binary system in sight. That would certainly raise some eyebrows. Another fascinating possibility involves the cosmic microwave background, CMB, the faint afterglow of the Big Bang itself. This ancient light bathing the entire universe holds a detailed map of the early cosmos, complete with tiny temperature fluctuations that seeded the formation of galaxies. If primordial white holes were actively spewing energy and matter into the early universe, they would have created localized perturbations in this primordial plasma. Could we detect anomalies in the CMB that are too precise, too structured, or simply too weird to be explained by standard cosmological models? Perhaps tiny, persistent hot sores or cold spots that don't quite fit the statistical distribution of quantum fluctuations, acting as fossilized evidence of a white hole's initial eruption. It would be like finding a perfectly circular ripple in an otherwise random pattern, a cosmic fingerprint left by an impossible event. But let's get even more speculative, pushing the boundaries of what we can imagine. What if the most profound evidence for white holes isn't in their direct emission, but in their gravitational influence? If the quantum bounce theory is correct, and some black holes eventually transition into white holes, that transformation itself could be a source of gravitational waves. These ripples in space-time, first detected in 2015, are our newest window into the most violent events in the universe. A black hole suddenly bouncing and becoming an outward-flowing white hole would be an event of unimaginable energy and might produce a gravitational wave signature unlike anything we've ever seen. It wouldn't be the typical chirp of two merging black holes, but something entirely new, perhaps a sudden, powerful burst followed by a prolonged oscillating decay as the new white hole stabilizes. Detecting such a signal would be a Nobel Prize-winning discovery, not just for white holes, but for quantum gravity itself. The implications of actually finding a white hole would be staggering, shaking the very foundations of our understanding of the universe. First, it would directly challenge and potentially overturn the cosmic censorship hypothesis. Remember, this hypothesis suggests that all singularities in our universe are censored, hidden safely behind an event horizon, preventing them from being observed directly. A white hole, particularly one formed in the early universe, could potentially expose a naked singularity, a point of infinite density and curvature directly visible to us, without the protective veil of an event horizon. If we could observe such a thing, our current laws of physics, which tend to break down at singularities, would need a radical overhaul. It would be like finding a crack in the very fabric of reality, forcing us to rewrite the rule book. Second, the existence of white holes could offer profound insights into the nature of dark matter and dark energy, the two greatest mysteries in modern cosmology. We know that dark matter makes up about 27% of the universe's mass, and dark energy about 68%, yet we have no idea what they are. Could primordial white holes, or their exotic remnants, contribute to the universe's dark matter budget? Perhaps they are a form of dark energy emitters, subtly influencing the expansion of the cosmos. It's a long shot, certainly, but in the realm of theoretical physics, no stone is left unturned. If white holes are constantly spewing out exotic particles or energy that we can't directly detect, they might be contributing to the invisible scaffolding that shapes the universe. And then there's the ultimate connection, the Big Bang itself. This is where the theoretical rabbit hole goes deepest. What if our entire universe is, in some sense, a white hole? What if the Big Bang wasn't just a singular, inexplicable event, but the outward eruption of a primordial white hole? This idea, sometimes called a cosmic reignition, or a white hole cosmology, suggests that our universe might be the exit point from a much larger, older black hole in another universe. Imagine that. The ultimate cosmic geyser, constantly expanding, constantly spewing out everything we see and know, from galaxies to stardust to us. This would mean our universe isn't just expanding, it's erupting. This concept offers a tantalizing, albeit highly speculative, solution to some of the Big Bang's thorniest problems. What was before the Big Bang? Where did all the matter and energy come from? If our universe is a white hole, then before might simply be inside a black hole in a parent universe, or a previous iteration of our own. It transforms the Big Bang from a mysterious singular event into a continuous process, a never-ending cycle of collapse and reignition. It's a universe that breathes in and out over timescales so vast they defy human comprehension. Of course, this is all incredibly theoretical, the very edge of our scientific understanding. We are talking about possibilities that stretch the imagination and push the boundaries of mathematics. But that's the beauty of it, isn't it? The universe is under no obligation to conform to our expectations. It is a canvas of infinite possibilities, and white holes, these elegant cosmic opposites, represent one of the most profound. The search for white holes is more than just a hunt for another exotic object. It's a quest to understand the fundamental nature of space-time, gravity, and the very beginning of everything. It's a challenge to our assumptions, a test of our theories, and a constant reminder that the cosmos holds secrets far stranger and more wonderful than we can possibly conceive. Will we ever find one? Only time and the relentless curiosity of humanity will tell. But the very act of looking, of asking these audacious questions, expands our minds and deepens our appreciation for the boundless mysteries that surround us. Okay, you've just wrapped your mind around the truly audacious idea that our entire universe, the vast cosmic tapestry we inhabit, might be the exit point of a primordial white hole. Think about that for a second. Our Big Bang, not a singular isolated event, but an eruption, a release, a cosmic geyser from somewhere else, from something else. My mind genuinely boggles at the implications. It's the kind of thought that sends shivers down your spine, the kind that redefines everything we thought we knew about beginnings, about origins, about the very fabric of existence. If that were true, if our universe is indeed the outward gush of a white hole, then every galaxy, every star, every planet, every living thing, including you, me, and this conversation we're having, it is a product of that cosmic expulsion. We wouldn't just be in the universe. We would literally be from a white hole. It shifts our perspective from being mere observers within a vast cosmos to being integral, emergent parts of a process so profound it defies easy comprehension. But here's the thing, the brutal, beautiful reality of science. Breathtaking speculation, no matter how elegant or mind-bending, isn't enough. We can dream of cosmic geysers and time-reversed universes. We can draw them on blackboards and simulate them on supercomputers. But until we have evidence, until we can point to something out there in the vast dark and say, that's it. White holes remain firmly in the realm of theoretical physics, a magnificent mathematical curiosity. So how do we bridge that monumental gap? How do we move from the elegance of Einstein's equations and the quantum weirdness of loop quantum gravity to the messy, exhilarating reality of cosmic observation? This, my friends, is the grand challenge. This is where the rubber meets the cosmic road. We've talked about potential observational signatures, the subtle emissions, the anomalous gamma-ray bursts, the peculiar hot or cold spots in the SEMBI, the unique gravitational wave chirps. But each of these, as we discussed, comes with a caveat. They could easily be explained by known astrophysical phenomena, or they might be so faint, so fleeting, that our current instruments simply aren't sensitive enough to catch them. It's like trying to find a specific unique snowflake in a blizzard, using a pair of binoculars from a mile away. The task is immense. Let's address the elephant in the cosmic room. Skepticism. And let's be clear, skepticism in science isn't a bad thing, it's a necessary thing. It's the rigorous gatekeeper that prevents us from chasing phantoms and ensures that only the most robust, evidence-backed ideas gain traction. Remember those critical issues we delved into? The inherent instability of white holes, the theoretical tendency to collapse if even a single photon tries to enter, the profound lack of a formation mechanism. How would such an object even come into being in our universe? The seeming violation of the second law of thermodynamics, locally decreasing entropy, and the challenge to the cosmic censorship hypothesis, potentially exposing a naked singularity. These aren't minor quibbles, they are fundamental challenges that demand equally fundamental answers. For many physicists, these issues make white holes unphysical, mathematically possible perhaps, but not reflective of reality. It's a bit like imagining a perfectly frictionless surface in everyday life. Mathematically possible, but practically impossible to achieve due to the intrinsic nature of materials. So for a white hole to exist, it would likely require a significant revision, or even an outright revolution, in our understanding of physics. This is where the quest for white holes intertwines with the grander, more ambitious search for a theory of everything, or at least a unified theory of quantum gravity. Our current physics, brilliant as it is fundamentally fractured. General relativity, our best description of gravity and the large-scale structure of the universe, breaks down at singularities, precisely where black holes, and by extension white holes, are most extreme. Quantum mechanics, our best description of the subatomic world, doesn't seamlessly integrate with gravity at these scales. To truly understand what happens inside a black hole, or how a white hole might form, or bounce from a black hole, we need a theory that marries these two titans of physics. We need quantum gravity, and theories like loop quantum gravity or string theory or others still nascent in the minds of brilliant scientists are trying to provide that bridge. It's within these cutting-edge theoretical frameworks that white holes find their most fertile ground for exploration. They become not just exotic objects, but potential test cases for these new, unproven theories. If a theory of quantum gravity predicts a stable, observable white hole, and we then find one, imagine the validation. It would be an intellectual earthquake of unprecedented magnitude. So what are the next steps? How do we push this boundary? First, we need to continue refining our theoretical models. We need to explore the parameter space of quantum bounce scenarios with greater precision. We need to understand if there are conditions under which a white hole could be stable enough, long-lived enough to actually be observed. Perhaps the primordial white holes, born in the chaotic crucible of the early universe, could have had conditions that allowed them to persist. We need to explore the mathematical possibility of different types of white holes, beyond the simplest Schwarzschild or Kerr solutions, perhaps ones with unique quantum properties. Second, we need to dramatically enhance our observational capabilities. The next generation of gravitational wave observatories like LISA, Laser Interferometer Space Antenna, which will operate in space, promise an entirely new window into the universe. Imagine detecting gravitational waves from the very early universe, or from the mergers of supermassive objects with such exquisite detail that we can discern the subtle ring-down signature of a black hole transitioning into a white hole. That would be a game changer. What about neutrino telescopes, peering through matter to catch elusive particles from extreme events? Or even entirely new types of detectors, sensitive to phenomena we haven't even conceived of yet? The technological advancements required are immense, but the history of science shows us that what seems impossible today often becomes routine tomorrow. Third, and perhaps most challenging, we need to develop new ways to distinguish a white hole from other known phenomena. This is the issue of degenerate signals. If a white hole produces a burst of energy, how do we know it's not a supernova or a magnetar flare, or some other exotic but known event? We need to predict unique, unambiguous signatures, cosmic fingerprints that only a white hole could leave behind. This requires even deeper theoretical work simulating what a white hole's light curve or gravitational wave profile might look like in excruciating detail, then cross-referencing that against every other known astrophysical process. It's a monumental task, a cosmic detective story of the highest order. This entire endeavour is a testament to the collaborative, iterative nature of science. It's not one lone genius toiling in an attic. It's a global network of brilliant minds, theoreticians pushing the boundaries of mathematics, observational astronomers designing and operating ever more sophisticated instruments, data scientists sifting through mountains of cosmic information, all sharing, debating, challenging, and building upon each other's work. It's a slow, painstaking process, often filled with dead ends and false starts, but punctuated by moments of breathtaking discovery that redefine our place in the cosmos. Why do we keep pushing these boundaries? Why chase after phantom geysers and time-reversed singularities that might not even exist? Because the universe is the ultimate puzzle, and every time we solve a piece, even a small one, it reveals a deeper, more intricate picture. The quest for white holes, whether it ultimately confirms their existence or definitively rules them out, forces us to confront the very limits of our understanding. It pushes us to develop new physics, to invent new technologies, to ask bolder questions. It's about the insatiable human curiosity, isn't it? That fundamental drive to understand how things work, why they are the way they are, and what else might be out there. The idea of a white hole, a cosmic fountain erupting matter and energy, is so profoundly counterintuitive, so wonderfully strange, that it compels us to explore. It's a mirror reflecting our own desire to understand beginnings, to explore the unknown, to challenge the established order. Whether white holes are eventually discovered, remaining elusive or definitively disproven, their theoretical existence has already enriched our understanding of space, time, gravity, and the extreme limits of physics. They are a powerful thought experiment, a cosmic what-if that stretches our imaginations and pushes the boundaries of scientific inquiry. The journey into the heart of reality is far from over. We stand at the precipice of new discoveries, armed with ever more powerful tools and ever more audacious ideas. The white hole, whether real or purely theoretical, serves as a powerful beacon, guiding us deeper into the fundamental nature of the universe. It reminds us that the cosmos still holds secrets so profound, so utterly mind-blowing, that they await only our persistent curiosity to be unveiled. And that, my friends, is why we keep looking up. We've peered into the theoretical abyss, haven't we? We've wrestled with the mind-bending physics of white holes, their mathematical elegance, and the formidable hurdles that keep them firmly in the realm of hypothesis. We've explored the whispers of quantum bounces and primordial eruptions, the faint hope of detecting these cosmic geysers. But now it's time to truly grapple with what their existence would mean. Because if white holes are real, if even one is ever confirmed, it wouldn't just be another fascinating astronomical discovery. Oh no, it would send seismic waves through the very foundations of physics, cosmology, and our understanding of reality itself. We're talking about a paradigm shift of epic proportions, a cosmic mic drop that would force us to rewrite textbooks, rethink our origins, and perhaps even redefine our place in the universe. It's a concept so grand, so utterly transformative, it genuinely blows my mind. Let's dive deep into these staggering implications, starting with arguably the most profound, the idea that the Big Bang itself was a white hole eruption. Imagine this. The universe, our vast, sprawling, magnificent cosmos, born not from an inexplicable singularity, but from the explosive expulsion of matter and energy from a white hole. Think about it. The Big Bang, as we currently understand it, posits an infinitely dense, infinitely hot point from which everything sprang forth. It's a concept that is incredibly difficult to visualize, and even harder to reconcile with the known laws of physics. It's a moment of creation ex nihilo out of nothing, which quantum gravity theories famously struggle to explain. But what if that nothing wasn't nothing at all? What if it was the interior of a black hole, perhaps one that existed in a previous universe, or even a different region of our own space-time? If we embrace the loop quantum gravity concept of a quantum bounce, where black holes don't collapse into true singularities but bounce back out as white holes, then the Big Bang takes on a whole new character. Suddenly, the Big Bang isn't an arbitrary, uncaused event. It becomes a consequence, is the grand finale of one cosmic cycle, or the explosive birth of a new one, all stemming from the time-reversed collapse of a black hole. Our entire universe, with all its galaxies, stars, planets and life, could be the outward gushing of a colossal white hole. This hypothesis elegantly addresses the initial singularity problem of the Big Bang. Instead of an infinitely dense point, we have a preceding phase, the interior of a black hole that undergoes a quantum transformation. It offers a potential mechanism for the universe's birth, linking its origin directly to the ultimate fate of its gravitational opposites. It suggests a cosmic continuity, a recycling of matter and energy on a scale almost too vast to comprehend. Think about the profound implications for the arrow of time. If our universe emerged from a white hole, does that mean our existence is, in some sense, a continuous expansion away from a moment of time-reverse collapse? It suggests a universe that is not only expanding but expelling, constantly pushing outwards from a point of no return. It's like we're riding the crest of an eternal cosmic geyser. This isn't just a different origin street, it's a different ontology for the universe. It shifts our understanding from a singular, abrupt beginning to a potentially cyclical, interconnected cosmic dance. Now, let's pivot to another monumental implication, the potential overturning of the Bohr cosmic censorship hypothesis. Remember this one? It's the idea, proposed by Roger Penrose, that nature abhors a naked singularity. That any singularity formed in our universe must always be hidden behind an event horizon, safely veiled from direct observation. It's a crucial principle because if naked singularities could exist, they would represent points in space-time where the laws of physics break down completely, where predictability vanishes. You could, in theory, send information into a naked singularity and have it emerge in an entirely unpredictable way, potentially violating causality and shattering our deterministic view of the universe. White holes, particularly primordial ones or those formed from quantum bounces, directly challenge this. If a white hole is truly a region from which matter expels, without anything being able to enter, then its boundary, its event horizon, is effectively a one-way outgoing surface. If such an object were to form without a preceding black hole phase, or if the quantum bounce somehow exposed the singularity at its heart before the full formation of an event horizon, then we might indeed be staring down the barrel of a naked singularity. Imagine the chaos. Physics relies on predictable cause and effect. If a naked singularity exists, it's like a cosmic wildcard, a place where anything goes. It would be a profound philosophical and scientific crisis, forcing us to rethink the very nature of information, predictability, and the fundamental fabric of space-time. It would mean that the universe isn't as safe and ordered as we thought, that there are regions where our most cherished physical laws simply cease to apply in a predictable manner. The cosmic censor would have failed, and the universe would be a much wilder, less deterministic place. But the implications don't stop there. White holes could also offer tantalizing insights into two of the greatest mysteries of modern cosmology: dark matter and dark energy. These enigmatic components make up about 95% of the universe's mass-energy content, yet we can't directly see or interact with them. They're the invisible scaffolding and the mysterious accelerating force that shapes our cosmos. How could white holes fit into this cosmic puzzle? Well, consider their properties. White holes are theorized to expel matter and energy. Could this expulsion be a source of previously unknown particles that constitute dark matter? Perhaps the extreme conditions within a bouncing black hole or the initial eruption of a primordial white hole could generate exotic particles that interact only gravitationally, fitting the profile of dark matter candidates. The universe might not just be filled with dark matter, it might be continually seeded with it from these cosmic fountains. And what about dark energy? This mysterious force is causing the universe's expansion to accelerate. Could the very act of a white hole expelling matter and energy, generating an outward push on space-time, somehow contribute to this cosmic acceleration? Could the quantum pressure or the unique space-time geometry around white holes generate a repulsive gravitational effect that mimics or contributes to dark energy? It's a speculative leap, certainly, but one that opens up entirely new avenues for understanding these cosmic enigmas. If white holes are constantly pushing outwards, they might be providing a subtle, pervasive energy that drives the universe's accelerating expansion. Ultimately, the existence of white holes would be a monumental step towards the holy grail of modern physics, a unified theory of quantum gravity. We currently have two incredibly successful yet incompatible theories: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the incredibly small world of particles and forces. They work beautifully in their respective domains, but they break down when we try to apply them together in extreme environments, like the singularity of a black hole or the beginning of the Big Bang. White holes, existing at the theoretical intersection of these two domains, are the ultimate testbed. Their formation, their internal structure, their event horizons, and their potential role in the Big Bang all demand a framework that can seamlessly weave together gravity and quantum mechanics. Theories like loop quantum gravity, which predicts the quantum bounce that could lead to white holes, would gain immense validation. Conversely, if white holes are definitively ruled out, it would force physicists to reconsider or refine many quantum gravity models. The very search for white holes, the attempt to understand their nature, pushes us to think beyond our current theoretical limits. It forces us to ask fundamental questions about the nature of space-time itself. Is it smooth and continuous, as general relativity suggests, or is it granular and quantized, as quantum gravity theories propose? White holes, with their extreme curvature and potential quantum origins, are the cosmic laboratories where these questions are put to the ultimate test. And then there are the more philosophical and existential echoes. If time can reverse, if matter can be expelled from a region where it was previously collapsed, what does that say about causality? Is time truly a one-way street, or are there hidden loops and detours in the cosmic highway? The very concept of a white hole as a time-reversed black hole forces us to confront our ingrained notions of how time flows and how cause and effect operate. Imagine living in a universe where the Big Bang was merely the outward breath of a cosmic entity, where the end of a star's life in one region might be the beginning of a new universe in another. It suggests a universe that is far more interconnected, far more dynamic, and far more cyclical than our current models often imply. It challenges our perception of ultimate beginnings and definitive ends, replacing them with an ongoing cosmic dance of transformation. The existence of white holes would fundamentally alter our cosmic narrative. It would mean that the universe is not just a stage for stars and galaxies, but a colossal engine of creation and destruction, where the most extreme gravitational phenomena are not just endpoints, but potential gateways to new realities. It would deepen the mystery, yes, but also illuminate new pathways to understanding the universe's deepest secrets. So when we talk about white holes, we're not just discussing a hypothetical object. We're talking about a concept that holds the key to unlocking the universe's deepest truths, its origin, its fundamental laws, the very nature of time, and perhaps even the destiny of everything we know. It's a journey into the unknown, a leap of faith into the mathematical elegance of Einstein's equations, and a testament to humanity's unyielding quest to understand the cosmos. The implications are truly staggering, and they remind us that the universe is far stranger and far more wonderful than we could ever possibly imagine. If the existence of white holes would challenge our understanding of time, causality, and the universe's ultimate origins and fate, suggesting a more interconnected and cyclical cosmos, then let's truly unpack what that means for us. What does it mean for our place in this vast, bewildering universe if these cosmic geysers are not just theoretical constructs, but active, fundamental players in the grand cosmic drama? Imagine for a moment the most audacious implication of all. Our entire universe, this sprawling expanse of billions of galaxies, this intricate tapestry of stars and planets, this very fabric of space-time we inhabit, might be nothing more than the grand, magnificent expulsion from a singular white hole. It's a concept that doesn't just reshape our understanding of the Big Bang, it completely redefines it. Instead of an inexplicable, infinitely dense point of origin that simply appeared, what if the Big Bang was, in essence, a white hole eruption? Think of it. The universe is a cosmic umbilical cord forever connecting us to an event horizon that we can never re-enter, only observe its outward gushing. This isn't just a different origin story, it's a profound reframe. The singularity, no longer just a terrifying endpoint of collapse for a black hole, transforms into a point of infinite density creation for a white hole. Is the ultimate cosmic geyser, constantly erupting, pushing out everything we know, matter, energy, space, and time itself. This idea, my friends, is nothing short of monumental. It transforms the Big Bang from a moment of seemingly spontaneous generation into an emergence from something, perhaps something that was once a black hole in another universe, or a point of quantum bounce within a larger, more complex cosmic structure. And if our universe is an eruption, what does that do to our understanding of causality and the arrow of time? We live in a universe where time flows relentlessly forward, where causes precede effects with an almost sacred certainty. A thrown ball falls because of gravity. A star explodes because it ran out of fuel. But if white holes are truly time-reversed black holes, spitting out matter and energy that from our perspective seem to appear without a prior cause in our observable universe, it suggests a deeper, far more complex tapestry of time. Perhaps time isn't a simple linear arrow, a one-way street from past to future. Perhaps it's a more intricate, interwoven pattern, with hidden connections that span beyond our current cosmic horizon. It's a truly mind-bending thought. Could the future of a collapsing black hole in one universe be the past, the very birth of a new universe through a white hole? This isn't just science fiction, it's a legitimate, albeit highly speculative question, posed by the mathematical implications of general relativity. It forces us to confront the possibility that our perceived linearity of time might be merely a local phenomenon, an illusion within a much grander, more fluid cosmic dance. This line of thinking naturally leads us to the tantalizing concept of the multiverse and cosmic cycles. If our Big Bang was a white hole eruption, what's to stop other white holes from birthing other universes? We could be living in one bubble within a grand, frothing cosmic ocean, where universes are constantly being born from the ashes or quantum bounces of others. This isn't just theoretical musing, it offers a mechanism for a multiverse, a way for it to actually function and propagate. It paints a picture of a cosmos that is not just vast, but endlessly generative, constantly renewing itself, creating new possibilities from the remnants of the old. The universe becomes a grand, eternal recycling plant, only on a scale that utterly dwarfs anything we can comprehend. It suggests that death and rebirth are not just biological phenomena, but fundamental principles woven into the very fabric of space-time itself. The implications for our understanding of dark matter and dark energy are also profound. These enigmatic components make up roughly 95% of our universe, yet we can't directly observe them. What if white holes, or the exotic physics at play within them, are a source or a sink for these mysterious entities? Could the energy expelled by a white hole contribute to the dark energy that's accelerating our universe's expansion? Could primordial white holes, born in the early universe, be a form of dark matter, interacting only gravitationally? It's a long shot, perhaps, but one that opens up entirely new avenues for investigation into the biggest cosmic riddles. And then there's the ultimate prize for theoretical physicists, the validation of quantum gravity. As we've discussed, many of the most compelling theoretical pathways for white holes, such as the quantum bounce, arise directly from theories like loop quantum gravity, which attempt to unify Einstein's general relativity with quantum mechanics. The observation of a white hole, or even the telltale gravitational wave signature of a quantum bounce, would be a monumental triumph. It would provide crucial empirical evidence for a theory of everything, bridging the chasm between the very large and the very small, unlocking secrets that have eluded scientists for decades. It would be a moment of scientific revolution, a paradigm shift that would ripple through every branch of physics. But beyond the scientific data, beyond the equations and the theoretical models, there's a deeper, more personal question that resonates with all of us. Why do we care about white holes? Why do we expend so much intellectual energy on something that might not even exist? The answer, I believe, lies in the inherent human drive to understand. This entire journey, from the first inklings of a black hole to the audacious concept of a white hole, is a testament to the human spirit of inquiry. We're talking about phenomena that are, by their very nature, almost beyond our grasp, at the absolute limits of physics. Yet we persist. We build grand telescopes, design intricate experiments, and conceive of theories that stretch the very fabric of our understanding. We are driven by an insatiable curiosity, a desire to know why we are here, how this all came to be, and what lies beyond the veil of the observable. The search for white holes isn't just about finding a new cosmic object, it's about finding a deeper truth about reality itself. It's about pushing the boundaries of what we think is possible, about questioning our most fundamental assumptions, and about embracing the sheer wonder of the unknown. The power of asking what if is immense. White holes might be real, or they might remain magnificent theoretical constructs, forever confined to the realm of mathematics. But the very act of considering them, of pushing the boundaries of what we think is possible, is where true scientific progress lies. It forces us to refine our theories, to question our assumptions, and to look at the universe with fresh eyes. It reminds us that the universe is far stranger, far more wondrous, and far more complex than we can ever imagine. It's a universe that constantly challenges our preconceptions, inviting us to shed our intellectual comfort zones and dive headfirst into the abyss of the unknown. The journey into white holes isn't just about hypothetical physics, it's about the very nature of existence. It's about the humbling realization that our universe, our reality, might be part of something infinitely grander, infinitely more mysterious. It's about the thrill of standing on the precipice of the unknown, gazing into the cosmic abyss, and daring to ask, what else is out there? And perhaps, more importantly, what else are we? The quest continues, pushing the limits of our knowledge, inviting us to dream bigger, to question deeper, and to never stop looking up. Because in that endless gaze, in that relentless pursuit of understanding, we discover not just the universe but ourselves. Imagine for a moment what it would truly mean to confirm the existence of a white hole. It wouldn't just be another astrophysical discovery, it would be a seismic shift in our understanding of everything. Our entire cosmic narrative, from the Big Bang to the ultimate fate of the universe, would need rewriting. The very fabric of space-time, the nature of singularities, the arrow of time itself, all suddenly up for re-evaluation. It blows my mind just thinking about the profound implications for quantum gravity, for our quest to unify the fundamental forces, for every assumption we hold dear about reality. But how do we move from these mind-bending theoretical possibilities to concrete, observable evidence? This isn't a simple matter of pointing a telescope and saying, "Aha, there it is." The hunt for white holes is one of the most challenging, ambitious, and frankly heroic endeavours in modern astrophysics. It's a testament to humanity's insatiable curiosity, our relentless drive to peer beyond the veil of the known and seek out the truly extraordinary. The core challenge, as we've explored, lies in their elusive nature. White holes are hypothesized to be incredibly unstable, potentially short-lived, and their theoretical emissions might mimic other energetic cosmic phenomena. If they're said primordial relics, they've been around since the dawn of time, likely dormant and difficult to distinguish from the background hum of the universe. If they're the quantum bounce aftermath of a black hole, the transition could be fleeting, happening in a blink of cosmic time, releasing a burst of energy that's gone almost as soon as it appears. So what exactly are we looking for? What are the cosmic fingerprints due of something that by all accounts shouldn't even exist? Scientists are painstakingly sifting through mountains of data, searching for the subtle, persistent whispers, or the dramatic, telltale roars that could betray a white hole's presence. One of the most promising avenues involves anomalous gamma-ray bursts, GRBs as so. These are the most powerful explosions in the universe, typically associated with the collapse of massive stars or the merger of neutron stars. But what if we detect a GRB that defies explanation? A burst of immense energy with no discernible precursor, no supernova or no merging compact objects, and no typical afterglow. This kind of naked explosion seemingly erupting from nowhere could be a signature of a white hole violently expelling matter and energy. It would be like a cosmic firework that just appears in the sky, brilliant and brief, leaving scientists scratching their heads. Then there are the gravitational wave signatures. This is where the concept of a black hole undergoing a quantum bounce becomes incredibly exciting. Imagine a black hole relentlessly drawing in matter, reaching its theoretical singularity, only to bounce back, transforming into a white hole and spewing everything out. This transition would send ripples through space-time distinct from the collision of two black holes or neutron stars. We'd be looking for a unique gravitational wave pattern, perhaps a sudden cessation of infall, followed by an outward pressure wave, a kind of cosmic thump and whoosh. Current gravitational wave observatories like LIGO and Virgo are already revolutionizing our understanding of the universe's most violent events. What if one day, amidst the cacophony of colliding black holes, they pick up a signal that simply doesn't fit any known template? That would be the moment our antennae perk up, wouldn't it? The SARM cosmic microwave background, CMB, also holds clues. If primordial white holes formed during the Big Bang, they might have left faint specific imprints on the CMB, the leftover radiation from the universe's infancy. Researchers are analysing the CMB for subtle temperature fluctuations, specific patterns, or even cold spots that can't be explained by standard cosmological models. It's like looking for a tiny, unique ripple in an ancient pond, hoping it reveals the presence of something truly ancient and profound. And let's not forget high-energy particle emissions. A white hole eruption could be a powerful source of neutrinos or cosmic rays, particles that travel across vast cosmic distances, carrying information about their extreme origins. Observatories like IceCube, buried deep in the Antarctic ice, or KM3net in the Mediterranean Sea, are designed to detect these elusive particles. An unexpected flux of high-energy neutrinos, seemingly uncorrelated with any known astrophysical source, could be another tantalizing clue. To pursue these faint signals, we rely on a sophisticated array of observational tools, both current and next generation. Our current arsenal includes gravitational wave observatories, LIGO, Virgo, CAGRA. These ground-based interferometers are constantly listening for space-time ripples. Their continuous upgrades and increasing sensitivity make them ideal for detecting the subtle bounce signals we're hoping for. X-ray and gamma-ray telescopes, Fermi, Chandra, Swift. Orbiting Earth, these telescopes are our eyes in the high-energy universe, crucial for spotting those anomalous GRBs and other energetic phenomena. They scan the sky with incredible precision, mapping the most extreme events. Radio telescopes, SKA, ALMA. These powerful arrays can detect the faint radio emissions from gas and dust interacting with extreme objects. If a white hole were to erupt within a dusty galactic environment, its interaction with the surrounding medium could produce a unique radio signature. MB satellites, Planck, WMAP. While their primary missions are complete, the data they collected is still being meticulously analysed, offering a treasure trove of information about the early universe. Scientists are constantly developing new algorithms to search for subtle patterns that might have been overlooked. Looking ahead, the next generation of observatories promises even greater sensitivity and reach. Space-based gravitational wave detectors. Like LISA, Laser Interferometer Space Antenna, will operate in a different frequency range than ground-based detectors, allowing them to probe larger black holes and potentially detect even earlier, fainter gravitational wave signals from a quantum bounce. Future SOG gamma ray observatories will boast unprecedented angular resolution and sensitivity, allowing us to pinpoint the origins of enigmatic bursts with greater precision. And as our understanding of particle physics evolves, we might even develop new types of detectors specifically tuned to look for exotic particles that could be byproducts of white hole eruptions. The search for white holes also intertwines with the broader quest for dark matter. Remember the idea of primordial white holes forming from extreme density fluctuations in the early universe? If these tiny ancient white holes exist, they could potentially contribute to the universe's mysterious dark matter component. While particle accelerators like the Large Hadron Collider (LHC) are primarily designed to discover new fundamental particles, their findings could indirectly inform our understanding of the extreme conditions under which primordial white holes might have formed, or even hint at exotic matter states that could be ejected from them. It's a long shot, but in physics, you never rule out unexpected connections. Of course, we must also consider the null result problem. What if, after years of dedicated searching, after building more powerful telescopes and refining our detection methods, we find nothing? That too would be a result. A persistent lack of evidence would force us to seriously reconsider the theoretical viability of white holes. It would either strengthen the arguments against their existence, or more likely compel us to refine our theories, adjust our expectations, and perhaps redefine what a white hole might look like or how it might behave. It's a continuous feedback loop between theory and observation, each informing the other in our quest for truth. The scientific community's persistence in this search is truly inspiring. It's a testament to our fundamental curiosity, our desire to understand the universe not just as it appears, but as it truly is, down to its most bizarre and extreme components. The stakes are incredibly high, promising to reshape our cosmic worldview. The journey is arduous, filled with theoretical puzzles and observational challenges, but the potential rewards, they are nothing short of universe-altering. The hunt for the unseen, the search for the impossible continues, pushing the very boundaries of human knowledge and reminding us that the cosmos still holds secrets far stranger and more wonderful than we can possibly imagine. Okay, so we've just scratched the surface of what white holes, if proven real, would mean for our understanding of the universe. We're talking about a seismic shift, a complete overhaul of some of our most cherished and fundamental theories. This isn't just tweaking a formula. This is tearing down the old blueprints and building something entirely new, something far more wondrous and complex than we ever imagined. Imagine for a moment the scientific community waking up to irrefutable proof of a white hole. The headlines would be immense, yes, but the internal reverberations, the quiet, profound rethinking happening in labs and universities around the globe, that's where the real revolution would begin. Let's dive deeper into those profound implications, because they truly reshape everything, starting with the very beginning of everything. The Big Bang, not a beginning, but a rebirth? Think back to the Big Bang. What is it really? It's our best model for the universe's origin, a moment of infinite density and temperature from which everything exploded outwards. But it comes with a problem, a nagging question that physicists have grappled with for decades. What came before, and what caused it? The Big Bang in its classical form represents a singularity, a point where our equations break down, where physics as we know it simply ceases to apply. It's the ultimate we don't know. But what if, as we discussed, our entire universe is actually the white hole eruption of a previous cosmic cycle? What if the Big Bang wasn't a unique, inexplicable genesis, but rather a quantum bounce from a black hole that reached its maximum compression, then rebounded, reversing its collapse to become a white hole? Suddenly, the Big Bang isn't a mysterious singular event, but a transition. It's not a beginning out of nothing, but a transformation from something else. The singularity problem? Potentially solved. Instead of an infinite point of creation, you have a moment of extreme but finite density that then expands. It's like the universe breathing in, then breathing out, an endless cosmic respiration. This idea, often explored in theories like loop quantum gravity, suggests that space-time itself has a granular atomic structure, preventing it from ever truly collapsing to an infinite point. Instead, it reaches a minimum volume, a Planck length scale, and then bounces. Consider the implications. If our universe emerged from a white hole, then there was a precursor. Perhaps another universe that lived and died, collapsing into a black hole only to be reborn as our own. This isn't just a cyclical universe. It's a universe that recycles itself. It suggests an eternal cosmic dance, where universes are born and evolve and eventually collapse, only to be reborn through the crucible of a white hole. My mind reels just contemplating the sheer scale of that. It shifts our perspective from a linear timeline with a clear start and end to an endless, interconnected tapestry of cosmic existence. Overturning cosmic censorship. A naked truth? Remember the cosmic censorship hypothesis. This brilliant idea proposed by Roger Penrose basically says that every singularity in our universe must be safely tucked away behind an event horizon. Like a cosmic curtain, the event horizon ensures we never get to see a naked singularity, a point of infinite density exposed directly to space-time, where all the rules of physics break down. The universe, it seems, likes to keep its secrets, maintaining predictability and causality. But a white hole, particularly a primordial one, could potentially expose a naked singularity. If matter and energy are constantly emerging from a point and there's no way to enter, that singularity could, in theory, be visible. It would be a point where causality is fundamentally broken, where effects might precede causes, where our understanding of how the information propagates through spacetime would be utterly shattered. If we were to observe a naked singularity, it would be a profound challenge to our current understanding. It would mean that there are regions of the universe where the laws of physics as we know them simply cease to apply, where predictability goes out the window. Imagine trying to predict the weather if, at any moment, a hurricane could spontaneously appear out of nowhere, without any preceding atmospheric conditions. That's the kind of chaos a naked singularity could introduce to our cosmic models. It would force us to rethink the very fabric of space-time and the fundamental principles that govern it. The universe, it turns out, might not be as modest as we thought. It might be willing to bear its most extreme and unpredictable secrets. Illuminating the dark. White holes as cosmic beacons. Now, let's talk about the universe's biggest mysteries. Dark matter and dark energy. They make up about 95% of everything, yet we can't see them, touch them, or directly detect them. Dark matter provides the gravitational glue that holds galaxies together, while dark energy is the invisible force accelerating the expansion of the universe. They are the great unknowns, the silent giants shaping our cosmos. Could white holes offer a clue? Some speculative theories propose that white holes could be a source of dark energy. Imagine a continuous, low-level expulsion of energy from countless primordial white holes, subtly pushing the fabric of space-time apart. Or perhaps they could be related to dark matter. Could a specific type of exotic matter, emerging from white holes, constitute the elusive dark matter? The connection here is largely theoretical, but it's incredibly tantalizing. If white holes could provide an explanation, even a partial one, for these cosmic enigmas, it would be a monumental breakthrough. It would be like finding a single key that unlocks two massive locked doors in our cosmic understanding. We're talking about linking the most exotic theoretical objects to the most pervasive, yet invisible components of our universe. That's a connection that could redefine our entire cosmological model. The Holy Grail, validating quantum gravity. For decades, physicists have dreamed of a unified theory, a single framework that reconciles general relativity, which describes gravity on cosmic scales, with quantum mechanics, which describes the universe on subatomic scales. These two pillars of modern physics are incredibly successful in their respective domains, but they fundamentally clash when you try to apply them together, especially in extreme environments like black hole singularities or the very early universe. This is the quest for what quantum gravity. The existence of white holes, particularly through the mechanism of a quantum bounce, would provide empirical evidence for quantum gravity. If we could observe a black hole transform into a white hole, or detect the unique gravitational wave signature of such an event, it would be the ultimate validation. It would mean that the quantum effects of gravity, which are usually too tiny to measure, become dominant and observable in these extreme cosmic laboratories. Imagine the excitement. It would be like finding the Rosetta Stone for the universe, finally allowing us to translate between the language of the very large and the language of the very small. It would be a monumental leap forward, a vindication for generations of physicists who have toiled to bridge this fundamental divide. It would fundamentally alter our understanding of space-time and gravity and the very nature of reality at its most basic level. This isn't just about white holes, it's about unlocking the deepest secrets of existence. The arrow of time and causality, a cosmic reversal. Perhaps the most mind-bending implication of white holes lies in their challenge to our understanding of time and causality. For us, time flows inexorably forward. We remember the past, we experience the present, and we anticipate the future. This unidirectional flow is often called the come arrow of time, deeply linked to the second law of thermodynamics. Entropy always increases, but white holes are, in essence, black holes played backward in time. If they exist, they suggest that time itself might not be as rigidly linear as we perceive it. If matter and energy can only emerge from a white hole, never enter, it's like a film running in reverse. This challenges the very notion of cause and effect. What if, in certain extreme cosmic environments, the arrow of time can be locally reversed or even cease to have meaning? This isn't just a physics problem, it's a philosophical earthquake. What does it mean for free will, for destiny, for the very structure of narrative in our universe, if the past isn't always immutable and the future isn't always distinct? It would force us to reevaluate our deepest intuitions about reality. Are we merely experiencing one facet of a multi-dimensional time-symmetric reality? The very thought sends shivers down my spine. It suggests a universe far stranger, far more fluid than our everyday experience allows us to comprehend. The human response, a universe transformed. So what would all of this mean for us, for humanity? The discovery of white holes would be more than just a scientific triumph. It would be a cultural and philosophical awakening. Our place in the cosmos would be recontextualized. If the universe is cyclical, if it's constantly being reborn, then our existence isn't a singular, fragile blip, but part of an eternal cosmic dance. It would inspire new art, new philosophies, new religions even. It would force us to confront the limits of our perception and the boundless possibilities of reality. The sense of wonder, already immense when contemplating the cosmos, would multiply tenfold. We would be living in a universe far more active, far more interconnected, and far more cyclical than we currently imagine. Our understanding of creation, destruction, and rebirth would be forever altered. The enduring quest. Why we keep looking. Even without direct observational proof, the very idea of white holes pushes the boundaries of our understanding. It's a testament to human curiosity, to our insatiable desire to understand the fundamental truths of existence. The pursuit of white holes, whether they are ultimately proven real or remain theoretical constructs, is invaluable. It forces us to refine our theories, to stretch our mathematical models to their breaking point, and to imagine possibilities that challenge our deepest assumptions. It drives the development of new observational technologies, pushing the limits of what our telescopes and detectors can see. It's why we build gravitational wave observatories like LIGO and LISA, why we launch X-ray and gamma-ray telescopes into space, and why we meticulously map the cosmic microwave background. We are always searching, always listening for the faintest whisper of the universe's most profound secrets. This quest is not just about finding answers, it's about asking better questions. It's about the journey of intellectual adventure itself. It deepens our appreciation for the universe's profound strangeness and complexity, reminding us that reality is often far more imaginative than anything we can conceive. So as we stand on the precipice of these theoretical wonders, we continue to search, we continue to ponder, we continue to build, because the universe in all its perplexing glory is waiting for us to uncover its next astonishing truth. And who knows, maybe, just maybe, that truth will be a cosmic geyser, erupting with the secrets of everything.